Good morning and welcome to this next lecture on sound and structural vibration. We have come to the end of these lecture series. So the last topic I would like to touch upon is fluid loading of vibrating structures. Now in the course, this is something, it's not that it has not been touched upon, it has not been spoken in the language of fluid loading. Okay, whenever we do coupled analysis, which we have done sound and structure coupled analysis for the classical Crichton's problem, and we have done it for the structural acoustic waveguide and also for the box, okay, panel interacting with the cavity. We have done coupled analysis. So fluid loading is there, okay, but this terminology was not used. So I will make a few comments on fluid loading. Okay, and we talk of fluid loading, that means basically a structure vibrates, okay, and then it generates pressure, and that pressure is obviously applied back on the structure. Okay, so now what is the nature of that loading? That is what is called fluid loading. What is the nature? What is the nature of that loading? Okay, so that means, is it like an inertia? Is it like a stiffness? Okay, or is it like a damping? Okay, so when you use a cycle pump, okay, when you use a bicycle pump to pump air into your tire, okay, you find it very difficult to pump, right? It's just a column of air inside. So the air is now acting as a stiffness. Okay, that's fluid loading. Okay, so we have two essential scenarios where the fluid is unbounded. So where the fluid is unbounded, and so you are trying to ask the question, is the radiator or is the structure an efficient radiator? Okay, there the fluid loading issue is whether it is inertial, okay, in which case the fluid locally exchanges energy with the structure and no far field sound is generated, or it could, the fluid loading could be in the form of damping, which means sound is transported away from the structure. So essentially that's the question we ask. Okay, the other scenario is when fluid is enclosed. Fluid is enclosed by the structure. It's a contained fluid. Okay, there we are mainly looking at how resonances are affected. How resonances are affected. And mode shapes are modified. Okay, mode shapes or new mode shapes appear. Mode shapes modified. Okay, so let me make some comments on this fluid loading. So we will take the case of an infinite panel first, the infinite panel or plate, okay, and then it's carrying a flexural wave. We have seen this repeatedly. Okay. Okay, so infinite 1D plate, radiating into half space. So the plate equation, okay, governing equation is D, the stiffness, del 4 eta the displacement, then mass per unit area del 2 eta by del T square, and I am exciting it with a excitation of this form. Okay, so I am providing a wave like excitation. It is not localized. The excitation depends on space. It's a continuous excitation. That's what this expression means. Okay, so that means I am forcing a wave on the structure, and therefore the structure in the steady state will respond accordingly. So we get the response is given by eta x comma t is an eta tilde e to the power j omega t minus kx x, which results in d kx fourth minus m omega square eta tilde is equal to f tilde. Now we define a wave impedance. It is the ratio of complex amplitudes. So we are saying complex in amplitude, so you understand what it means, of force per unit area and complex velocity amplitude. Complex velocity amplitude. Complex velocity amplitude. Okay, so what we mean is z tilde plate is equal to f tilde by j omega eta tilde, which is minus j over omega d kx fourth minus m omega squared. Okay. So now kx is the forced wave number. Kx is the forced wave number. Okay. Now the free bending wave number, in the plate is, let's call it kp. Okay, I've been using kb and kp interchangeably, so kp. Okay, omega square m by d to the power 1/4. Okay. And what is that? Okay, so if now kx becomes equal to kp, you can see that z tilde, then z implies z tilde wp goes to 0. So the impedance goes to 0. It's like resonance, right? Kp is naturally what the panel likes, the free wave number, and kx is what we are forcing into the plate. So if those two become equal, the impedance will go to 0. Okay. Further, if kx is greater than kb, okay, Then the impedance is spring like, whereas if Kx is less than Kb, then the impedance is mass like. Okay, you can check that out. In one case you will get j omega something like m, in the other case you will get minus j by omega spring. You will get expressions like this. Okay, so now we can introduce some damping also. We can introduce damping. Okay, and the damping is introduced as a complex Young modulus. Okay, so the E whatever is there is made complex with a loss factor, and therefore along with damping we can write this as minus j by omega dkx fourth minus m omega square plus, and therefore it will have a similar form of the stiffness eta over omega. Okay, so that's the plate wave impedance. Now the next step is that we now assume the plate to be in contact with a fluid. Okay, and so this is my geometry again. This is y direction. So the pressure field is two-dimensional. My x direction, so I have a wave moving on the panel or plate. So this is now my acoustic half space. Okay, now suppose again a force of the form as before is applied again to the plate, okay, from below. Okay, and plate carries kx because it's forced. Plate carries kx. Okay, and therefore the x wave number of the fluid is also kx. Okay, so what will ky be? So we should know this by now. Ky will be the difference between squares of the acoustic wave number and the x direction wave number. And then we know by now the sign is decided by whether k is greater or k is less than kx. Okay, sign from physics. So if kx happens to be less than k, then we take the positive real square root. Okay, what does that mean? That means it means that plane sound waves propagate in the medium. I should mention that all this I am taking from this book by Fahy. Okay, Sound and Structural Vibration by Fahy. Propagate in the medium. Okay, and power is taken away from the plate. Okay, why is that? Because my P x comma y comma t is some amplitude e to the power j omega t minus kxx minus square root of k square minus kx square into y. So this j and this negative real number mean propagation in the y direction, and we don't allow the negative sign. So negative sign is here not allowed. We had two signs here, right, plus and minus. So in this case the negative not allowed. Okay. On the other hand, if it happens that kx is greater than k, okay, then we have to choose the negative imaginary value, negative imaginary kx square minus k square. Okay, why is that? Because we have p x comma y comma t is equal to p tilde e to the power of j omega t minus kxx, but kx is now greater, so I have to choose a minus j square root of kx square minus k square. Let me see. No, this should be plus finally into y. I have minus ky y with a j, that is the starting point. So with a minus j I have to choose a negative imaginary wave number, minus j square root of kx square minus k square into y. So this goes, and I have j square. So this gives me, j square gives me a negative, so I have a negative wave number, and this is a real number. So this is a decaying wave in the y direction. Otherwise it will blow up in the y direction at infinity. Okay, so that's why the negative sign here has to be chosen. Okay, now what is the impedance? Fluid impedance at the plate surface. Plate surface. Okay, which means the pressure at x y equal to 0 t, okay, is given by omega rho 0 b tilde e to the power of j omega t minus kxx divided by plus or minus square root of k square minus kx square. Okay, we have seen this before. The velocity is j omega eta tilde. Okay, just computing pressure over velocity through the Euler equation. Okay, so the wave impedance okay, of the fluid is given by plus or minus omega. I have suddenly used rho 0. It's okay. So it's a fluid density. So I've either used rho for the fluid or rho 0 for the fluid throughout. Okay. So let me keep it rho for consistency. Okay. Rho is the fluid density. So omega rho, okay, by k square minus kx square to the power of half. Okay. Now when kx is less than k, then the fluid impedance is rho 0 c. Again I have this tendency, rho c by square root of 1 minus kx over k whole squared. Okay, it's real, and therefore radiation occurs or radiation damping occurs. Okay, that is, the plate works on the fluid. And the fluid carries power away from the plate. Okay. Now yeah, further at an angle so you get plane waves at an angle cos inverse kx by k. So the fluid is a damper. Causing radiation damping. Okay. Now when kx is greater than k, then the z tilde w is j rho 0 c by square root of kx over k whole squared minus 1. Okay. That means the phase speed kx is greater, so lambda x is smaller. So phase speed of the forcing is less than the speed of sound. That means the impedance is reactive. Okay, so if how an inertial also and inertial. Why inertial? If we open this expression out, okay, what do we get? We get is equal to j rho 0 c into k divided by square root of kx square minus k square, and this k is omega by c. So this c cancel, so I get j omega rho. I'm again using rho 0, which is okay. So rho 0 or rho, please take it as fluid density, mean fluid density, rho by square root of kx square minus k square. So you have a j omega times some positive real number, so it's inertial. Okay. Now when a force is applied, let me take this. When a force is applied to an infinite plate, in contact with a fluid, then what do we have? Now we have to do a fully coupled analysis. So we have d del 4 eta by del x fourth plus m del 2 eta by del t square is equal to f tilde e to the power of j omega t minus kx x minus p x 0 t. Okay. So now what we will get is, we will get structural impedance from here, we will get fluid impedance from here. Okay. So there is a common velocity at the interface. So we tilde z tilde w plate is equal to f tilde minus v tilde z tilde w f, or f tilde by v tilde is equal to z tilde w plate plus z tilde w fluid. Okay, just a note here that if there is fluid on both sides, and same, then the z tilde wf will be twice z tilde wf. Okay. Now we have seen that in Crichton's problem, okay, in Crichton's problem, let's say below coincidence, okay, the free bending wave number kb or kp becomes kp plus delta. Okay, so this we actually computed. Okay, but as we are doing a very descriptive analysis prior to actual computations, so we will use a different language or thought process. That is how to analyze this without, if we have not done a detailed calculation. The time is up for this lecture. I will continue in the next class. Thank you.